Today we're going to take a trip to the playground in order to observe moving reference frame kinematics. We're going to participate in a seemingly simple event, passing a ball across a common playground merry-go-round. And we're going to see some strange yet predictable effects that arise from the moving reference frame.
In our first shot, the camera is attached to the ground in the stationary frame. Notice that the ball travels in straight lines. In our second shot, the camera is attached to the merry-go-round, rotating. Notice that the ball curves to the left on every pass. Let's try to explain what we just saw. First, a minor point is that the velocity of the ball in the stationary frame is the relative velocity imparted plus the velocity of the person pushing the ball. This determines the direction of the velocity. The more interesting results are in the rotating frame. As far as the curved path goes, it can be explained by the Coriolis component of acceleration seen in the moving reference frame acceleration equation. We assume that the merry-go-round has a constant angular velocity, and the ball begins with the velocity relative to the merry-go-round, vrel, towards the center of the merry-go-round. Since there is no net force on the ball, we assume its acceleration to be 0 in the stationary frame. In the rotating frame, we attach our observer a set distance above the center of the merry-go-round, approximately where our camera is located. When we set up our acceleration equation, we see a number of terms drop out as zeros. Now we solve for the relative acceleration in the moving frame. We see that it involves a component that will always be in the radial direction, resulting from the ball not having the same centripetal acceleration as it would to stay on that point on the merry-go-round, as well as a term from the Coriolis component. This component will always be normal to the relative velocity, and thus cause a curve. From the cross product, if the merry-go-round is rotating clockwise, the ball will appear to curve to the left. Finally, we will show what the relative acceleration is when the ball is initially released. As you can see, there is a term for the lack of centripetal acceleration in the x direction, as well as the Coriolis component that causes the curve in the y direction. Given this information, we would expect the path to look as shown. Knowing this, let's look back one last time at the video. As strange as the path may seem, it actually follows what our moving reference frame kinematics equations would suggest. Generally speaking, rotating reference frames can offer some very interesting and counterintuitive phenomena.